Okay, so I'll probably start working on an intro from now because people who are watching any one video do not know about the existence of the other videos. So yeah, I am finishing this book as the intro, and I am going to try to attempt every exercise. And this is the latest one. I have done every exercise, every section before this, except for the supplementary exercises of chapter section 11. So I'll do that hopefully soon enough. I am work. Okay, I have not worked on it. I should start working on it. Oh well, yeah. So yeah, let's get started. So yeah, we're starting with the product topology and subspace and order topology. Yeah. So from this point onwards, we're going to pretty much define them with the basis elements, right? So the basis elements are suitable to define a topology because they create a topology. We've discussed all that. And yeah, so we have two topological spaces. That's how we're going to create a product topology on XY. Or should we start it? Okay, we'll start it order. Yeah. Okay, hang on. Yeah. Okay. So we have a simply ordered subset, anything, X and a simple order. That's so we've discussed simple orders before, right? Yeah. And from simple orders, we can define four types of sets, which is I'm just writing one of them, but yeah, X uh, X is greater than equal to A and less than B. Yeah. So we can define four types of sets with various closed and open intervals. And yeah, from that we get so yeah, we can define open intervals this way. And the basis for the order topology on X from this simple order, which we have to know from context or it's given to us, is simply the set will have all elements of the form in comma B. So all open intervals. And if there exists the least element, then all elements of this form. So this is the least element. And if there exists the largest element, then all elements of this form. So this is these two elements are conditional, but the open intervals form the basis. And now let's check that it is indeed a topology. So we just need to check that it's a basis actually, because we already discussed that we can make a topology from a basis. And that's simple. So yeah. So for all x in X, well, let's see. This is by totality, there's going to be a comparison, right? So what does that mean? That means if X is the least element, we're good. Anything. If X happens to be the greatest element, then we're also good. And if there is no least or greatest element, then there exists an element A less than X and B greater than X. And simply put, we can just use that as a basis and we're done. So for all X and X, we have a basis as the first condition. For the second condition, we need the intersection of two basis elements. So we just check the formula and see what happens, right? So there are a couple of cases, and I'll let you work through them, but essentially all of them result in an ordered pair. And sorry, I mean, it is an ordered pair, but open interval. Yeah. So essentially, if A is less than, you get the idea. We just intersect them this way and or this way, or let's see, yeah, this way. I mean, yeah, it just splits around, but essentially you take the least of the biggest of these ones and the least of these ones, and then you get the intersection. Yeah. And then you can define the set this way, and it may be empty. But the empty set is a part of the topology precisely because this is also an open interval. So this is the empty set and it's an open interval. So the whole set and again, it's on the basis, so it doesn't matter. You can always have an empty intersection. So yeah, that forms the topology. So now what? Now, yeah, there are some examples. We're going to cover them in detail in the exercises. So that's it. Yeah, rays are defined in a similar way. You just so B is just not existent. If B is non-existent, then we've gotten the ray essentially, because infinity is supposed to represent unbounded. So if infinity is some number that's greater than every number. So if X can go till infinity, it's not bounded by any number. So yeah, infinity is just a convention. You define it through formulas. That's pretty much it. You can't define it as a number. And formulas are, we've discussed it. Okay. Yeah. And so since any open interval can, so for an open ray, if there exists a smallest element, then this is also an open ray. Observe that, right? Or a closed ray if you want to close this up. But yeah, open ray. So this is an open ray if A naught is what the smallest element, because well, it's yeah, you check the definition, right? I'm not writing it here. And same thing with B naught if it's the largest element. So there, so if the open rays are to be, so observe that the union of all open rays is union of any, so the, yeah, the collection of all open rays is equal to X. So by definition, it forms a subbasis, and from any subbasis we can make a basis, right? So we just need to check that the subbasis formed from the set of all open rays is precisely the basis of the order. So we already got all sets of these types. They are precisely open rays, right? Now we need to check if open intervals can be formed from intersecting open rays, and that's pretty easy. You just take A comma infinity and B comma, sorry, minus infinity comma B, right? And yeah, we'll be done. Yeah, so note that we are essentially figuring out what the intersection of two sets here is from essentially the definitions of the simple order, right? So we're still very much using the simple order in defining the set. So we need the transitivity and all of those axioms. And yeah, from those axioms and a set, we can define a topology. And yeah, yep. Okay, so if you want a sub-basis for the set and not a basis, the open rays are a sufficient kind. But yeah, ultimately, if you have a simple order, you can define it. Yep. Okay. Yeah. Now the product topology. So first of all, we need two topologies, right? So we already have x and tau prime, I'll write it this way, and y and tau prime, right? So we have two topologies already. And then, yeah, so it's not mentioned, but yeah, we have the open sets and the topologies are implicitly mentioned. In fact, I'll stop writing them from this point onwards. So yeah, essentially, we call the sets themselves the topology for convenience, and the open sets are, yeah, the members of the topology. And they are, so don't forget them that all the topologies are power sets, are subsets of the power set. But yeah, we forget a lot of the set theoretic rigor to have like to have more practical uses, which we are going to do. Anyways, yeah. So we also have the Cartesian product of x and y. So we have the power set of x and x cross y, and yeah, we can also have the set of all Cartesian products of the open sets and x and y. So u belongs to tau and v belongs to tau prime. Right. Okay, the topology was useful here, but yeah, you can write u is open and x in the, and means the same thing. So yeah, and this is how we're defining the product topology. So yeah, we can define it this way because this makes a basis. So yeah, you just have to check that it's a basis again. And that's pretty simple. U cross V intersection U2 cross V2. So these are both open by hypothesis. And we just have to check that not open, sorry. These are both members of the basis element. And we have to show that their intersection is also a member, since we're defining this to be the entire collection of basis elements. Right? Okay. Now, what? Yeah, so this we've proven it in section 1, but essentially this is the same thing as U1 intersection U2, which is open by definition as X is a topology, or X has a topology. And yeah, same thing with V1 intersection V2. So they're both open sets, and therefore they're members of this space. And for every X, we have an open set because X and Y are open. So there you go. We can just we have a basis element for each X and Y, and that's precisely X cross Y. That's also an open set. So yeah. Now what? Now So this is a basis, and we can have a topology. There's that. Now, yeah, so we can have a better basis for this topology, essentially. We can have a basis from the bases of the topology, right? That's what the next theorem is telling us. So we already have a basis from the open sets. Is it a basis of the topology itself? Yeah, it's a basis. We only need a, yeah. But we just have to check that, yeah, so if we show that the basis condition is theorem 13.2 is satisfied, which is the, containment thing, then we know that the topology from the basis, what, u cross v is finer or not finer. We can check whatever we want from with respect to the topology from the B cross C, where B is the basis for the topology of X and C is a topology for the basis for the topology of Y, and we're just essentially multiplying the elements. So if we can show that this is finer than the product topology and vice versa, then we'll be done. Yeah, I don't think it goes for the finer both ways. Both ways. Mm-hmm. Okay. Yeah, it's going both ways, I guess. So, okay. Yeah, so let's go both ways. So, given an open set of x plus y, so now we have defined that. Let's see. It's for any x and w, right? So, I'm going to actually call it z now because z is equal to some x plus y, right? So, let some z be a member of this w, right? I'm cheating. Oh, well. Yeah. Okay, right. Sorry. So by definition, there exists U cross V that contains it, and by definition, there exists B contained in U such that X is contained in it, and Y is contained in C, contained in B. So X cross Y is contained in contained in B cross C, which is contained in U cross V. This extends from again section one. So what now? Now no, all we've gotten from this is that tau prime is actually finer than tau, right? From theorem 13 point. Now, what about the other one? Actually, yeah, it contains it, doesn't it? No, that's just fine. Hmm. Hmm. So for that, yeah, I'm gonna have to think. Yeah, okay, my bad. So I was applying the wrong theorem. I mean, I ended up proving the fineness thing also from the theorem, but yeah, so it is finer by theorem 13.3, not 13.2. And to show that it's a basis for the topology of x cross y, we're using theorem 13.2, which is the C collection one, right? The C collection and every member of C x belongs to C contained in that one. So W is an open set in C. So first of all, we have to check that this is a. So the other inclusion comes from the fact that this is a collection of open sets. So every B cross C here is actually open. So that's all we really need. And that's, yeah. So actually what we just proved from this one is that tau is finer than tau prime. And the other one follows directly from the fact that tau, every member of tau prime is an open set. That's another way of looking at it. And and yeah, you can also trivially apply the fineness criteria because since every open set is a member here, you can just take that open set and you get this containment condition. So that's another way of proving it. And I was approaching that way, but I felt like something was off, and that was because I had to. So there are both are actual legitimate ways of solving the theorem. You can use the fineness criteria, which I suspect I feel is more useful, and you can also use the theorem directly, which is just find a containment thing. So, but yeah, for the other one, we're checking that it's a collection of open. So you revise the theorems and their applications as you go along. Okay, now we have a subbasis for this topology as well, and that's going to be a lot more fun because it allows us to generalize the product topology on a general product, right? We're going to have a general product soon, and we can generalize the product topology using the subbasis. And yeah, for the subbasis of x cross y, which is only a binary product, we are going to have no problem at all. And that's in from induction, the box and product topology aren't different, and we're going to discuss all that later. So yeah, let's get to it. So we have the projective map, and essentially we have some coordinates, so we have to specify that. And for that, we need an index set. We can't have a projective map without an index set. But for the Cartesian product, we have the index set as 1, 2, right? Whatever, right? So because we have the index set, we can define the projection on any member of this index set. And yeah, essentially phi of x cross y, phi sends any member of x cross y to x, and pi 2 sends any x cross y to the member to y. So essentially u cross v is sent to u or to v by pi 1 and pi 2. So yeah, the projective map is, yeah, it's a rule of assignment, all that you can check. And it's an open map because, well, this is an open set in the product topology, and it's sent to an open set in y and in x, which are topologies we're assuming, right? I mean, we have defined this from the topology, of course. So yeah. So now what? Yeah, it's an open map, and you define it. Yeah, and it's surjective because yeah, you take any member, you're going to have an open set containing it. By definition, you can take y as an open set, and yeah. In fact, yeah, sorry, we're not even taking open sets. You're just taking the projection, and you just take for every y you take x cross 6 y naught goes to y naught, and so for every y naught you have that, and similarly for x naught. So it's an open surjective. You'll also see that's also a quotient map, but the only useful quotient topology which you're going to study later you can get from this map is the product topology. So maybe, I'm not completely sure, but yeah. Okay. So we're going to discuss continuity soon, but essentially, yeah. So it's clear that the x can vary and essentially be any member of x to get this y naught, right? So in general, the inverse image phi 2 inverse of y naught is equal to x cross y naught, right? And that holds for any subset of y in general. So phi 2 inverse of v is equal to x cross v. Yeah. And pi 1 inverse of u is equal to u cross y, right? That's pretty easy to see. You just need to go with the definition of inverse images, which is, there exists b in this such that f of b is equal to c, which belongs in this, right? That's the definition. So you follow along that, and then you'll see that this entire set, you can check the inequalities both ways. That's how you rigorously prove it. But we don't really care about that here. We've discussed it so extensively, we can skip all of that. Okay. So yeah. So now using the inverse images, we can find a definition of a subbasis, right? So yeah, it's easy to check that pi inverse u and u being open is an inverse image. That's pretty easy. Hang on. U open in X. So this alone is actually by definition a subbasis for the product topology. Actually, no, not for the product topology, but for the topology. Yeah, it's a subbasis for a topology, but not product. It's actually the subbasis for a topology that's homeomorphic to the X topology, which means it's actually homeomorphism is isomorphism, but for topology. That's giving you a rough intuition, but we're going to discuss that as well when we discuss continuous set. So a lot of things can be introduced right here. Anyways, so this is a base subbasis for a topology, and so is phi inverse. Yeah, phi 2 inverse V. V is open in Y. So these are subbases, and you can easily check that the union of two subbases is a subbasis. And what now? Yeah, so, and observe that the union is X cross Y, so this is a subbasis. And to show that it's a subbasis for the topology of X cross Y, you need to show that there to any finite so okay. So first you have to check that all of their members are lying in the basis, which they are because they're open sets. So we're done, right? And the other thing with so one inclusion is done, right? So the topology made from this as a subbasis is coarser than the topology, the product topology, right? That's already done. For the other way, we need to check essentially that we can get an open set through a finite intersection, and that's trivially true because let's say you want U naught cross V naught. Well, U naught cross X is sorry Y is given to be an given to us, right? And so is V X cross V naught, right? So their intersection is well U naught cross V naught, and both of them are subsets of each other. So V naught is a subset, U naught is a subset, right? Okay. So we got any open set that we want, any base, any member of the basis of the product topology that we know of, and we can get it. And precisely because of that, this forms a subbasis for the topology of this. So the other inclusion is proved this way from the fineness criteria. Yeah. Actually, no, I think we didn't use the fineness criteria here. We just directly use the definition of inclusion. Okay. Okay, time for the subspace topology. Yeah. So here the book defines it through the topology itself. So it defines all the collection of open sets. So you have to check its topology this time instead of you know a basis. So how is it defined? Well, so Y is a subset of X. X is a topology. Yeah, and U is an open set of X, and you collect all the open sets and then you intersect them all with Y, and that's the well that's the topology. And phi and y are trivially in there because x intersection y is equal to y. So x is in there, so y is in there, right? And phi intersection y is equal to phi. So phi is also in there, right? And note that we're defining the subspace topology as power sets, a subset of the power set of y. So they're all collections of subsets of y, not x. Yeah. Now for finite intersections, yeah. For finite intersections, we have a u1 intersection y intersection from I is equal to 1 to n. And this is a finite intersection. And this is the same as u1 being intersected, intersection y. And this is open by definition. And these two are equal because how do you prove that these two are equal? Let's see. Actually, yeah, you can prove it by induction, right? That at least for a finite case, yeah, prove it by induction. Since we can show that for a pairwise intersection is true, so yeah, prove it by induction. Anyways, this is an open set, and by definition, this is an open set, so this thing is an open set. So the finite intersection of open sets is an open set by through the definition of the topology on X, since X has a right. And same thing with arbitrary unions. In fact, even this is true for arbitrary cases here. But yeah, this actually follows from the distributive property of intersection and at least it's true pairwise. We're not. Let me check about the arbitrary case. Let's see. Right. Let's see. That's it, right? Yeah. Okay. So we're going to have to use the quantifier definition. So let's see. If we take any member here, it's going to lie in one of them, and that's an open set. So no, it's yeah. So is this equal to essentially union alpha, U alpha intersection Y? Right, that's the question. So it's going to lie in Y no matter what that's there. And is it also going to lie in all? So yeah, it's going to lie in one of these here, and that has to lie in here and here, so we're done. And if it's lying in one of these here, it's going to lie here too, so it's going to lie here. Yeah, you can check it orally. It's a quantifier thing. Okay, so we also have a basis for this topology, and we're going to prove it using theorem 13.2. So essentially, you just take the basis elements of X and you intersect them with Y, and then you got a basis topology, a basis for the topology. Yeah. Okay, so you take any open set U intersection Y, that's going what the open sets are going to represent. And since for U, for all X in U and Y, so it's also going to lie in U, we have a basis element that's a subset. So X is also going to belong to, well, X does belong to Y here. So X is going to belong to the intersection Y, subset of U intersection Y. And since it's a collection of open sets, since every basis element is an open set, Y by definition, that's kind of so any basis for X has to be a collection of open sets. There is kind of an if and only if. You can check that. And yeah, because of this criteria, since it's a collection of open sets, this makes a basis. So yeah, it's all about the fineness criteria. So you can use theorem 13.3 directly, or you can check using subsets. That's what the foundation of all these proofs are. Okay, so we've got a basis, we've got the topology itself. Now we have to, okay, that's an interesting theorem. Let's prove it. Let Y be a subspace of X. So I'm just going to write this as a subspace topology, and it kind of becomes implicit that we have a topology on X, and then we're just intersecting on the same with Y. Yeah. If U is open in Y, and Y is open in X, so Y is a subset, so it can happen. Then U is open in X, so that's pretty easy. Let's see. U is equal to V intersection Y. V is open in X, right, by definition. And this is open in X. Therefore, this is open in X, but this is U, so we're done. Yeah, sometimes the rules are really short. Okay. Yeah, so the product topology is, yeah, so we can have a subspace of a product topology this way. So since the subset thing exists, we can have a subspace this way. And essentially everything lines up is what the proof is. And the reason for that is precisely because U intersection A cross V intersection B is equal to U cross V intersection A cross B. So yeah, because of that, precisely because of that, we get to carry over all the open sets. Because this is the subspace topology using this one. and this is the subspace topology and then made into a product. So these are two different things, but since every member is equal, the sets are equal, and therefore the topologies are equal. Okay. Yeah, but for order topologies, we don't have a similar subspace thing. So let's study that. And the examples in that, am I going to cover them? Okay, I won't cover the dictionary order thing. Okay, I'll do both. Why not? Yeah, so I read a bit and see. So yeah, okay. So the first one is it matches up essentially, and that's all that's discussed. And if we take this set to be y, then essentially, okay. So what we have as the open sets in in the order topology. So for the open race kind of category, we have two and some number between 0 and 1, right? And essentially it's going to include two and all numbers, and it's going to include so can it be only one? Yeah, it must include one as well, essentially, because yeah, it's going to be an open ray, right? And any open ray that's going to include two has to include it cannot be one comma two, right? Or can it? Hang on. Okay, yeah, never mind. So my bad. It has to be open here because if it's closed, then 1 comma 2 is an open set, and the example breaks down. So for the example to not break down, it has to be open, right? For closed one, the example does break down. Yeah. Anyways, no, is this a counter example of convex set? I'll think about it. It might be. I'm not sure. Okay, it isn't. It isn't convex. We're going to get to that. But yeah, the point is, since one is not even included, we can't have this as an open interval. And in the order topology, if we take this as a set and we have this the regular order on it, we cannot get an open set that contains only. But in subspace topology, since 3 by 2, comma 5 by 2 is open, that intersected with y, which is the singleton 2, is open, so there's a difference. Okay. And for the dictionary order, for the ordered square, which is essentially defined as the dictionary order on 0, comma 1 cross 0, comma 1, also called I naught square. Since if we take the dictionary order on R2, this is an open set, right? But the intersection is an open set in the subspace topology by definition, but it's not a open set in the order topology since it has this closeness here, and this is not the Lie set. So yeah, pretty much. Okay, now a convex, a subset of X, and X is an ordered set, is said to be convex if for all A and B in it, um, and without loss of generality is less than B. Let's see. A comma B, which is defined with respect to elements of X, is completely contained in Y, and that means Y is convex. So intervals and rays are convex. That's easy to check somewhat. You can use the transitivity and all that stuff. Yeah. Okay. Now, yeah. So if Y is convex, now we have to prove that they are the same topologies, the order and subspace topology. So if you take the order topology of Y as a restriction of the order on X, that's one topology. And if you take the subspace of Y, the subspace topology of Y on the order topology of X, that's another topology. And uh, with Y being convex, the theorem says that they're the same. So note the different topologies here. And yeah, so the book just focuses on the subset because subspace topology because Y is first noted as a subset. set of X. Then we, yeah, okay. So what the book is using to prove this theorem is essentially that if we take the subbases of Y in both the topologies and show that the subbases are equal, then the topologies are equal, right? So it has to be the subbasis for the topology. And yeah, since we proved in question 5 that the subbasis always gives a unique topology, we will be done. So yeah, we have to show that the subbases are equal. So in the order topology, we have what? Open rays essentially, right? Yeah. And I have to study this proof. Okay, so I worked a little bit on it, and there were a lot of insights that I got. Okay, so I'll start over and let's hope I can explain everything in one go. All right, yeah. So Y is a subspace of X, and has the order topology. Now, Y can have an order topology on its own by respecting the subspace of X, and Y can also have a subspace topology by just taking the intersection of all the open sets of X. And we want to show that the topologies are equal when Y is convex. Yeah. So first of all, I'll prove directly that the order topology is always contained in the subspace topology, and the examples suggest that because the examples always showed an open set in the subspace topology that wasn't open in the order. So how do we show that? Well, yeah. So before showing that, we're using question 5 essentially. So we have a subbasis for a topology Y, and we have another subbasis for another topology of Y, right? And essentially, to show that one topology is contained in the other, we're showing that one subbasis is contained in the other. And that's an application of question 5, essentially. And that's one theorem. The other theorem, so it's essentially a bigger version of the fineness theorem, right? Yeah. So I mentioned in theorem 13.3 that if B prime happens to be contained in B, then tau prime is contained in tau, right? But the other implication doesn't hold because we don't have a basis all the time, right? So we're doing a similar application with question 5, but on the subbasis. That's one thing. And the other thing to note is that the book has mentioned a theorem. So I used a theorem without stating it. And that is as follows. If S happens to be it happens to be a subbasis of X, right? Then the collection of S intersection Y is also a subbasis of the subspace topology. And essentially that comes down to the fact that so we get the basis elements from finite intersections by definition. And we also get the very same basis element by finite intersections due to the distributive law of the intersection, right? So it all works out. And that's the theorem it used implicitly. Implicitly, that's the word, right? I hope. Yeah. So that's one more thing. Yeah, now we are almost there. So this is going to be the subbasis for the order topology of Y, and this is going to be the subbasis for the subspace topology of Y. And I just mentioned what those were, the topologies. Yeah. So in generality, this is contained in here. Let's prove that. So what is the subbasis here exactly? It's going to be an open ray, right? I'm just going to write open ray of Y, and that's subbasis for the order topology. Okay. So what is that defined as? That's defined as y is greater than or equal to some a in Y, and Y is also in Y, correct? Okay. But as you can see, the formula lines up completely. And so in fact, you can even add Y belongs to X. So Y has to be a subset of something, right? So no problem making it of X. And what we get? We get this part is an open ray in X. this part is y, and this part is already there. So that's how we get an open ray in X intersecting y. So the formulas line up completely. And because the formulas line up completely, the intersection just comes out. That's the definition of intersection, actually. So what does that mean? That means any open ray of y is an open ray of X intersecting y. And that's precisely the subbasis of the subbasis for the subspace topology. So we have proven that this containment is there. And this does not require convexity at all. So one case happens all the time. The other one requires convexity. And I haven't looked into it fully. Oh well. Yeah. Oh well. Yeah. I hope you didn't see that. Yeah. Yeah. So for the other case, we take an open interval. So we take the basis, right? This intersected is y. Okay. Now we have to show that this is an open ray in y, right? If we show that this, which is the member of subbasis of the subspace topology, is an open ray in y, then we'll be done with it. Both ways, of course. So how do we do that? Let's see. This is essentially defined as X belonging to X. X is greater than or equal to A, right? And their intersection is going to be this intersection. Yeah, and X belongs to Y. Okay. So we have two cases. A can be in Y and cannot be in Y, need not be. So if A is in Y, then what do we get? We get A is in Y and every member greater than A is in also in Y. Or is also in the, what do we call it? This thing, right? It's also in there. Yeah, so essentially every member greater than A, so every member greater than A is going to lie in Y. Why is that? Because of convexity. That is because, yeah. So if X is in Y and X is greater than A, then everything in between is going to lie in that. And yeah, and if that set doesn't have a largest member, then Y is also not going to be bounded. And if it is bounded, then yeah. Hmm, how do we use convexity rigorously here? I do want to spend more time on this. So, hmm, okay, if A is belonging to Y, so it's given to us, right? Now, let Y belongs to X and Y greater than A. Yeah, I mean okay, the formula does line up. So no, okay, now we have to show it's an open interval in Y. Yeah, so Y is going to be greater than A and it's going to lie in Y. And okay, the reason it's an open ray will be because of convexity, essentially, because yeah. So if it okay, if Y has the largest element, then it's going to be there in Y. That's easy to check since Y is greater than or equal to A and it's in Y, right? And essentially A comma B naught is going to be there, and this is precisely an open array. So that's the case. Now, if Y doesn't have one, then for all, it's essentially going to be the union of all such B naught, right? So any B, so we can take the B naught as the set of all B elements that are greater than A, and it doesn't have a largest element by assumption, and we can take their unions. So this union will be an open ray, right? Why will it be an open ray? Because it doesn't have a null. So it cannot be bounded, and yeah. So this will be an open ray, and why? Because of convexity. Because everything in there is going to be contained in Y. That's the whole point. Containment is important. Yeah. I've tried to explain what the book brushed over, I would say. Yeah. Mm-hmm. Yeah. Why is it an open ray of the order set Y? I mean, it is by definition. But I do, yeah. So in this case, convexity was used. I tried to make be as rigorous as possible. That's the best I guess. And yeah, the same thing holds for minus infinity, comma a, right? So that's also an open range Y, and essentially the subbasis is contained, so it's contained both ways, so the topologies are the same. And yeah, so I've done till question. I've done the supplementary exercises till question 2, so hopefully I'll be done soon enough. And I guess share. I don't know if how to give an outro. Just yeah, I guess I could use a share, and I don't care too much about the growth of this channel at the moment because I'm more focused on finishing the book. But yeah, I mean, if somebody could use these lectures, then share it to them. So yeah, let's start the exercises now.